the idea of partial fractions. So when you have a fraction involving rational functions or polynomials, how do we approach it? Well, if the degree of the numerator is greater than or equal to the degree of the denominator, first thing you do is a polynomial division. Now once you've done that, so once you've got that degree less than the degree of the denominator, factorize the denominator. Now for a linear factor, then we create a fraction, a over x minus a, so for a fraction for every linear factor. If it's a multiple root or a multiple factor, then we write a fraction for each of the powers. So power n, I'd have a over x minus a, b over x minus a squared, and I'd keep going to whatever it is. The other possibility is we get a quadratic that can't be factorised. So in that case, the numerator I'll make a linear function, so a degree of 1 less, so ax plus b. But every polynomial we know can be factorised down to be a combination of linear and quadratic factors, so that should cover every situation. Okay, let's do some. Well, this is a nice easy one to start off with, there's no factorising to be done. So x squared on x plus 1, if you have to, do your polynomial division like this, x and x squared, that goes x. Remainder minus 1, remainder 1. So we can rewrite that as x minus 1 plus 1 over x plus 1, and we get something very simple to integrate. Add 1 to the power over the power for the first two, and then we get a log function for the fraction. Let's do one where we have to actually factorise. So 3 on x squared minus x, so the denominator is x minus 1. So let's work it out. I'm going to put a fraction for each of those. So I'll have a over x and b over x minus 1. When I combine these two fractions together, I should get the 3 on the x minus 1. So the question is, what is a and b? Well, I could multiply by the common denominator, x minus 1, to get rid of the fractions. And then just do clever substitution to make life easy for myself. So x equals 0 will get rid of the b. It won't be there. So now I know a is negative 3. And then I can get rid of the a by making x equals 1, so b would end up equaling 3. I now know what a and b are. I can go back to my integral, again, simple log functions. You're going to be expecting a lot of log functions if you think about it, because you're going to have a linear factor on the bottom and a constant on the top. That's what we're going to end up with. That's how we've set it up. So you get up with a whole heap of logs. Minus 3 log x plus 3 log x minus 1. I'll combine those two together because you've got the same coefficient out the front. Well, one's negative, one's positive, but essentially the number's 3. So it makes sense to combine that into one log using our log laws. Okay, let's go for a quadratic denominator. X squared minus 3x minus 10. Does that factorise nicely? Multiply together to give negative 10, add together to give negative 3. Of course, 2 and 5, yeah. There you go. So we'll set it up. Okay, good. Let's use clever substitution. I'll make x equals negative 2, b becomes negative 3/7. I'll make x equals 5, a is 10/7. So I can now rewrite it. I suppose I could have pulled a 7th out, that's common there. But again, we're going to have two log functions. You'll notice this time I didn't bother combining them together. I mean, I could have, because I got the common factor of a 7th, and I could have pulled the numerators in by making them the power of the thing in the log. Nah, too much work. dx on x cubed plus x. This time we have a linear, but the other one is a quadratic. So I'll have bx plus c on the top. Again, clever substitution will find us a, b and c. If x equals 0, I'll end up a equals 1. If x equals I, you see, we can use complex numbers to our advantage. If I use I, that's going to get rid of the a, because I squared is negative 1. And I end up with negative b plus ci is 1, real part must equal the real part, imaginary part must equal the imaginary part, so b is negative 1, c is 0. There we have it, and log functions yet again. Even that quadratic one is a log because we've got an x on the top. So we've got log x minus a half of log x squared plus 1. You'll notice I didn't bother with the absolute signs on the x squared plus 1 because that's got to be a positive number. Wow, this one's already been factorised for us, but you see we've got a repeated root here, x plus 1 squared. So I have a fraction for each of the repeated roots, a on x plus 1, b on x plus 1 squared, and I've got a quadratic, so linear function on top. All right, what will I use first? I'll make x equals -1. That's going to make the cx plus d disappear. It's also going to make the a disappear. We get b as -1/2. If I use x equals I, I'll get -2c plus 2di is I. So that tells me c is 0, d is 1/2. I still have to find b. Well, I'll just pick an easy number now to substitute in. But I know what b and d are, so I can sub that in as well. As it turns out, a is 0. That's what I have to integrate. There's that du on u squared idea, the first one there. I know where that goes to. And the second one actually is inverse tan, isn't it? So I'll have half times 1 on x plus 1 plus inverse tan of x. There is another way of finding a, b and c very quick, rather than having to write all that out. Okay, so an alternative way of doing it is what's known as the cover-up method. And this is what you do. If I wanted to find a in this expression here, I will substitute into this. You'll notice I have covered up, if you like, the x minus a factor. You see, this is the fraction I'm working out. The denominator is x minus a. So I've covered that up. It's like it's not there. So I get a will be equal to, substituting that a in, I'll get function a on a minus b, a minus c, whatever that works out to be, that is what a is. Then I could do the same for b. I will cover up the x minus b and substitute in b. That'll be what b is. Then I could do the same for c, and so on, and so on, and so on. So let's go back to the ones we did before. So on this one, if I wanted to find a, I'll cover up the x and I'll substitute in, well, it'll be 0. And so I'll get 3 on -1. A is -3. Now to work out b, I'll cover up the x minus 1 and I'll substitute in 1. Essentially, it's whatever makes the denominator 0. That's what you're substituting in. And so we get 3. There's our answer. Here, this was the next one we did. Okay, I'll cover up the x minus 5 and I'll substitute in 5. I get 10 on 7. I'll cover up the x plus 2 and substitute in -2. I'll get -3/7. And if we take advantage of complex numbers, we then can apply this idea to the quadratic factors as well. I want to find a. I will cover up the x, substitute in 0, and I get 1. Now I will cover up the x squared plus 1. What makes the denominator equal to 0? Well, I would. So substitute in, I get bi plus c, so the numerator, when I substitute in, equals 1 on I. 1 on I, the reciprocal of I is of course -i. Real part equals real part, imaginary part equals imaginary part. So what would I have done for this one? For a, cover up the x minus 1, substitute in 1. Alright, the next one's a little bit trickier. What makes 4x squared plus 1 equal to 0? Substitute in a half I. Play around with the right hand side and eventually get it. Hey, I'm not saying it's going to be quick every single time, but that's why you have a combination of ways of doing things. So those simple linear ones, bang, comes out straight away. Maybe for these more involved ones, it's easier to just, oh well, I'll pick some sensible numbers and substitute in, get some simultaneous equations, whatever. You just use whichever method's going to be the quickest for you. So B ends up being -3, C is 1. Now when it's maybe not, we'll see, multiple factors. So this one here, what would I have done? To work out A, that's nice, cover up the x plus 2, I'll get -2. Here's where I now have a problem. I've got x minus 1 and x minus 1 squared. We're substituting in what makes it equal to 0. So if I cover up the x plus 1 squared, am I getting the answer for C or am I getting the answer for B? It's going to be the highest power. Because you see, if I'm trying to find B, I'm covering up x minus 1. But that denominator really is x plus 2, x minus 1 times x minus 1. So I'm only covering up one of them. And when I substitute in 1, I now get 0 on the bottom of the fraction, which is a problem. So it will only find the higher power. So it's C that I'm going to find. So how on earth do I find B? Well, now I'll go back to a simple substitution and get that. So I'll let x equal 0. And there we go. We know what A is, we know what C is, and we get that B is 2. What about this one? Here we go. I've got x plus 1 squared, so this will find me b. B's minus a half. Now, ci plus d, I can cover that one up. Again, a little bit more work, not as bad as that other one, but we get ci plus d is a half. I now have c and d. X equals 0, I'll always pick it unless I can't because of domain issues, because it's just so easy to work with. A plus b plus d ends up being 0, so a is actually 0, and I get that one as well. The quadratic denominator that can't be factorised. Okay, well, the a I can find, not a problem. What makes x squared plus 4x plus 5 equals 0? Well, to find the good substitution for this, complete the square and we'll find the substitution. It's going to be minus 2 plus I I'll use. So minus 2 plus I will make this disappear. Sub it in. A little bit of work, but we get there. Real part equals real part, imaginary part equals imaginary part. So b is negative 1. Negative 2 plus c is also negative 1, but b is negative 1. c is negative 3. Another one of those ones where perhaps not the best method for that one, but you know, still a fair bit of work to do. All right, so that's partial fractions, the idea of doing that.